This video is for Physics 12, Chapter 6. It's Lesson 3. We're going to review power calculations. Some of the things that we've seen actually in Physics 11 we're going to take another look at. And so just first of all, a little reminder of just the way we look at electricity. Right? We've got our battery, which is going to force electricity through a resistor. If you want to install an ammeter, it's got to be in series, in line with the circuit, so you can monitor the flow. And then voltmeters are wrapped around devices to watch for changes in voltage, either up or down. And we've got our trusty little shopping analogy where we can say that the coulombs are like customers and the batteries are like banks that give dollars to the customers instead of joules to the coulombs. And an ammeter records customers per second, and then a voltmeter is like a wallet inspector. It takes a look at dollars per customer that are gained or lost at a resistor or at a battery. Okay, so this is a little review of electrical power and energy, some stuff that we've seen in Physics 11. At the beginning, don't worry about writing anything down. Let's just take a look at a little story, and then we'll go and draw some notes after that. So imagine you've got a motor, and it's going to lift up some mass. Maybe it's half a kilogram, maybe it's 500 grams, and you want to run some electricity through that, and then we're going to monitor the wattage for this motor. So I'm going to connect up a battery, right? That way I can actually force some electricity through the motor. If I want to monitor the current flow, I'm going to have to install an ammeter in series. I'll have to break the connection and then insert that ammeter so I can monitor the flow, the amps, the coulombs per second. And if I want to monitor how many volts are getting to that motor, then I would want to put a voltmeter on in parallel. It just, while the circuit's running, reaches around things to see what the gain or the loss in voltage would be. Let's imagine that this motor manages to lift this mass up pretty far, okay, several stories. It's going to go up 16 meters, and let's say it's on the clock, little stopwatch there. Let's say the whole thing gets done in 4 seconds, okay? And again, you're not writing any of this down for the moment, okay? We'll start to take a look at it here as we go through this, okay? So this is the notes that you will want to write down. Here's my story for what that looks like in my mind. I've got a battery, which is just a couple of lines, one bigger than another. So these are notes that you'll want to write down. Got my ammeter in series, and then around my motor, I'm going to grab a little voltmeter to check the drop in voltage there. Now, it's kind of hard to draw a motor. You can just draw a resistor, just a little zigzag path like that. That'll be fine. All right, so we've got our circuit all ready to go, and we can monitor the current, we can monitor the voltage. I'm going to just make up some values here. Let's say that the voltmeter records a 12-volt drop. Okay, we're going to lose 12 volts on that device, on that motor. Now, I know we say volts and we write volts, but really that means 12 joules per coulomb. The ammeter, let's say that it's actually running at 2 amps. Okay, so that's what we say, that's what we write down, but in your mind you want to be thinking of that as 2 coulombs every second. So we know how many joules are on board every coulomb, and we know how many coulombs are going through every second. And again, let's say that the time for that motor to lift it is just measured at 4 seconds. Okay, the equation for power, saw this actually in Physics 11. You can calculate power by going just I times V. That's kind of the classic version of the power equation. And I don't normally put the units in, but I'm going to put them in on this example. So my current, it's 2 amps, but I'm going to think of that as coulombs per second. And my voltage, 12 volts, but I'm going to think of that as joules per coulomb. And you can see that the coulombs are going to actually cancel. You've got one in the numerator, one in the denominator, and so when we actually go and multiply those together, we end up with just joules per second, which is perfect. That is exactly what watts are. So I didn't need to use the time at all. I can just use the I and the V, multiply them together, and it looks like I'm actually consuming electricity at 24 joules every second, 24 watts. Now, if you want to figure out energy, then you'd have to take power and multiply by time, okay? Because power is energy divided by time. And just looking at the units, it works beautifully, okay? 24 joules every second for 4 seconds. That's going to give me 96 joules of electrical energy going into that motor. Hey, just a little review. Jot this down. We talked about efficiency back in Physics 11. Let's take a look at this motor's efficiency. So generally speaking, efficiency is the useful energy out. What did it do for you? What did it accomplish? Divided by all of the energy that you had to put in. So here, the useful energy out is some potential energy gain, and all the energy in is the electricity, the electrical energy that went in. So for me, I would go MGH for my calculation of energy out, and then power times time for my energy in, which I already know actually is the 96 joules. So my calculations would look something like that. I've just got my MGH up on the top. Remember, we said it would go 16 meters up. That was the story that I made up. And that MGH calculates how much energy went where you wanted it to go, but not all of it went where it should have, right? And if you actually look at the denominator, 96 joules went in, but you don't have 96 joules in the numerator. And so we have this efficiency of 81%, 81.7%. You can quote it as a percent. Some people just quote it as a decimal. And that's totally fine too. So yeah, power, you can just go I times V in order to find out what the power is. Now, pencils down for a second. Don't jot this next stuff down. We'll summarize it in a better way in a minute. There are two more formula that you can use for finding power in addition to IV. Here's one situation that happens all the time, and again, you don't need to write this down. We'll summarize it in a minute. Sometimes people forget to install the ammeter, but if you've got a well-labeled resistor, so you know the resistance value, you can actually go and say, hey, no big deal. I don't have to worry about not knowing the I. I could calculate it with Ohm's law. P is equal to IV, so I can just go V over R times the V. And if you bulldozer that together, you get power equals V squared divided by R. Okay, so that's just another option in order to find the power in the circuit. But be careful. Make sure you're using the voltage drop at that resistor. And there might be multiple resistors, and you can't use the battery's voltage in that case. So make sure you're thinking, hey, what voltage is happening right there? Okay, now, again, don't write this down. We'll summarize it in a minute. Lots of times people say, well, I don't need that new equation. I can just go and find the I. So yeah, here's an example where you don't really need it. If I told you the battery was 8 volts and it's only connected to a 4 ohm resistor and asked you for the power, you could use V squared over R and you'd be done really fast, 16 watts. But you might be thinking, I don't need that though. I want my life to be simpler. I could go and find the current first. 8 volts divided by 4 ohms, it's 2 amps. Hey, now I know the current. And then go back to classic IV, 2 times 8, 16 watts. Yeah, you're right. You didn't need to use V squared over R here. But watch this. As your teacher, I can take that question and rearrange it in a way where the only way in is to use V squared over R. So here's the exact same story. It turns out it is going to be the 8 volt battery, but you don't know that. And it's going to be that 4 ohm resistor. And then I'm going to ask you, hey, what battery should I go and grab in order to get to 16 watts? You can't actually jump in with Ohm's law or I times V. There are actually too many unknowns. You don't know what the voltage is or what the current is. So this is the only way to get into the story because you couldn't start with either Ohm's law or P equals IV. And now it's actually not too bad. You know, 16 is the power, 4 is the resistance. It's pretty quick to solve. Multiply by 4, you're going to get a 64 over there. Take a square root. Yeah, it's 8 volts. But that's a story where you have to actually use V squared divided by R. So it's not only handy, sometimes it's actually necessary. Here's the other story. Sometimes people forget to install the voltmeter. They've got a good ammeter and a well-labeled resistor, but no voltmeter to measure the drop. And so you're sitting there going, well, how would I do P equals IV? I don't know the V. You could use Ohm's law in order to calculate algebraically what that voltage drop would be. And then if you just bulldozer that together, you get power equals I squared R. So it's a third option for finding power. If you're going to use it, make sure you know how much current's flowing through that resistor. If you've got a circuit, we'll see in later days, that has branches in it, and you might have one main current coming out of the battery, well, if it splits up and you're trying to worry about a branch current, make sure you know that lower value for that branch current that's going through the resistor you're looking at. Same thing again. Just wanted to show you that sometimes you can avoid this entirely. So here's a story. You know it's 5 amps. You know it's a 4 ohm resistor that it's going to go right through. People ask you for the power. I squared R is the fastest way there. The answer is 100 watts. And you might be thinking, but I don't need that I squared over R. I don't want to complicate my life with extra equations here. Yeah, you can get away without it. You could do Ohm's law, find out that it's a 20 volt drop. And then calculate the power with the classic IV calculation. And yeah, you get 100 watts. But watch this. As your teacher, I'll just turn this around. It's 100 watt power dissipation on a 4 ohm resistor. It's a 20 volt drop. It's 5 amps. Same story. But what if I word it like this? Hey, how much current should I put through this 4 ohm resistor in order to have 100 watts of heat come off? 100 joules every second. There's no way to start with V equals IR because you don't know V and you don't know I. And there's no way to start with P equals IV because you don't know V and you don't know I. You have too many unknowns. And so the only way into this question is P equals I squared R. And if you do that, it's actually pretty simple. Power is 100, resistance is 4. You would divide both sides by 4 to get a 25. Take a square root. Yeah, the current's 5 amps. So sometimes it's just a convenient thing, and other times it's totally necessary to use this I squared R. Okay, let's summarize that because I said we were going to go pencils down for a bit here. You'll probably want to make a little note of this. So you've got these two extra power formula. The V squared over R is great when you don't know the I, and the I squared R is great if you don't know the V. Right? So we're gonna use those a fair bit, not only for convenience. Sometimes it's out of necessity. Okay, I'm going to go through 4 examples here for just calculating power, and then we're going to talk about power for your house, kind of a 5th example. This story says a battery is connected to a 10 ohm resistor, and the power is 24 watts. Great. And then they ask you, what would be the power dissipated if the resistor is replaced with a 20 ohm resistor? Okay, so I'll tell you where I'm going with this. Sometimes people get a little bit confused because they wonder, well, should I be going P equals V squared divided by R, or should I be going P is equal to I squared R? And what's interesting is the resistance is actually in different locations for these two equations. One is in the denominator and one is up in the numerator. Now looking at the story, it looks like the resistance has gone up by a factor of 2. And if I use the first equation, if I use this one, a bigger value for R would suggest that the power would be smaller because it's in the denominator. But if I use this equation, a bigger value for R suggests that the power would be bigger. And so it kind of looks like, it's a conflicting story and there's no perfect way to do this, but it is totally doable. And the issue is all about, what's staying the same. And the answer is the battery. I'm using the same battery. So in trial number 1, I've got this 10 ohm resistor. That's a pretty bad looking resistor, but I've got this 10 ohm resistor. And then in trial number 2, I'm going to connect up that same battery to now a 20 ohm resistor. The currents are going to be different in these stories. Okay, there's actually more current here than there is there. So I would actually avoid using this story. It's actually it's tough. There are competing effects going on in that story. Instead, you're better off looking at this equation here. Power is equal to V squared over R, because in this story you can go, yep, big check mark on the V, same battery. And now when you tell me, oh, the resistance is actually going to go up by a factor of 2, the power is going to go down by a factor of 2. That's what that fraction will do with the math. So instead of being 24 watts, it looks like we're going to have 12 watts in this story. Okay, so it's all about being careful with what's changing and what's not. Now, I have seen some students do this. Some students say, well, I really like this power equals I squared R. I want to use this. And yeah, I saw the resistance went up by a factor of 2. And then they say, oh, but then the current's going to go down. And you'd have to be so careful, right? If you knew the current was going down by a factor of 2 and then noticed that it was squared, then you could say, oh, okay, that's like 2 downs by a factor of 2 and then 1 up on the resistance by a factor of 2. But I would avoid that because you're going to see stories soon where maybe the resistance goes up by a factor of 2 and maybe the current goes down, but only a little bit. So that's competing effects where you have up and down arrows trying to change things in different directions. If you can avoid it, it's good to do that. So I would avoid that in this case. All right, next one. Got a battery connected in series now to 2 resistors at the same time, a 10 ohm resistor and a 20 ohm resistor. And they tell you a little bit about the power in the 10, and they want to know about the power in the 20. Okay, so you'll want to draw yourself a little story that looks like this. We've got one resistor, and then another resistor, and then we go back to the battery. And so this is 10 ohms, and this is 20 ohms. Now we're going to go over circuit theory in a little bit, but the key thing for when you've got something connected in series, you've got one value for the current the whole time. So all through that circuit, there's the same I. So if you've got the same I, this is a perfect time to use this equation. Power is equal to I squared R. Because now what you can do is put a big check mark on the I and say, well, that's not changing. And now in trial number 2 for that 20 ohm resistor, that resistor is actually bigger by a factor of 2. So actually we're going to get a power that's bigger by a factor of 2. I don't need to do all the math, which we'll go over next day actually. I can look at it and say, oh, the power is going to go up. It won't be 24 watts anymore. The second resistor is going to have 48 watts. Okay, so just trying to make good choices for which equation to grab. Okay, that can save you a lot of time. Okay, a couple more of these. Got a 100-watt Canadian light bulbs designed for 120 volts here in Canada. You take it to Germany where the voltage is 240. What would the wattage there be? Okay, well, I could go to the trouble of finding the resistance of that light bulb. I'm going to see if I can avoid it. Instead, I'm just going to think about this as like checks and arrows, trial 1 and trial 2. I've got my one light bulb. So there it is. And in Canada, I've got 120 volts, and there's some resistance here. But if you go to Europe, you're going to find the voltage there is double what we have here. So now that battery has gone up to 240 volts. But it's the same light bulb that you've put in your luggage and taken to Germany. In this case, the resistance is the same. The currents would be very different. There's a much bigger I here than there would be here in Canada because of that bigger voltage on the same light bulb. So instead of worrying about the I's, I'm going to try to just work with these V's here. I would go with V squared over R. And I'd say, oh, this is great. It's the same light bulb I've taken to Europe. Big check mark on the R. But the voltage in Germany and Europe is going to be twice as big. And since you're squaring it, well, that's going to be quadratic. That's going to be 4 times as big. So it looks like the power is going to go up by a factor of 4. Okay, so just, again, trying to make smart choices on V squared over R or I squared R for which one to use. So it won't be 100 watts. It won't even be 200 watts. It would actually be 400 watts, right? Probably very unsafe for that light bulb. Probably wouldn't last very long. Probably would burn out. Okay, one more of these. Let's say you have some good old Canadian 100-watt and 60-watt light bulbs, and they're connected in series to 120 volts. You do not normally connect things up in series like that. That's very unusual. And it's asking, what's the wattage of each light bulb? This time I am going to go and find the resistance of each one, okay, just before I get rolling here. So power is equal to, I'm going to go V squared divided by R. I've got my 100-watt light bulb, and it's getting 120 volts here in Canada. And I'm just going to find out what the resistance for that light bulb is. Just grab my calculator here. Okay. So it looks like we'll go 120 squared divided by 100 in order to get there. Okay, so that's 144 ohms of resistance. Okay, that's for that light bulb. But then there's this other light bulb, this 60-watt light bulb. Okay, let's go and check it out. Power is equal to V squared over R. What about 60 watts with 120 volts? Okay, so there I'd go 120 squared divided by 60. That light bulb actually has 240 ohms of resistance. Now don't worry if you can't totally remember how to do this from Physics 11, because we're going to go over this next day. But now I'm going to try to wire up some circuit. This is not the way you're supposed to wire things up. Got 120 volts here. I'm going to put in my 100-watt light bulb and then my 60-watt light bulb. So the 100-watt light bulb was 144 ohms and the 60-watt light bulb was 240 ohms. Okay, well, we will go over all of this in the coming days, but here the total resistance would be 144 plus the 240. So we've got 384 And now I would go and figure out the total current coming out of that battery. 120 volts divided by 384 ohms. 0.3125 amps. All right. Now, all of those resistors, both of them, are going to have the same I flowing through there. So now we can go and check out the actual powers. So I'm going to go I squared R because they both get the same I. For that 144 ohm resistor, that 100 watt light bulb, I would be going 0.3125 squared times the 144. Okay, so this light bulb that was rated at 100 watts, it's nowhere near 100 watts, it's like 14 watts, it's really dim. And the other light bulb, it was actually rated at a lower brightness, a lower wattage, 0.3125, and it's 240 ohms. Okay, 0.3125 squared times 240. It's actually brighter, right? It's 23 watts. So this is why we don't wire light bulbs up like this in your house, right? It just wouldn't work out very well. We will go over all of those kinds of calculations next day too, so don't worry about that. Last thing, electrical power and energy in your home. We don't typically use watts. They're too small. We often use kilowatts. And instead of saying, oh, well, you ran that device for 5 seconds, now often you leave things on for hours. So when we multiply I and V together, we're actually going to be creating a story that's not actually going to be in watts. We're going to go kilowatts. And then when we multiply by time, we're not going to multiply by seconds, but we'll go by hours. 1 kilowatt hour, it is like a George Foreman grill, 1,000 watts going for 1 hour. That's a lot of energy. It's 1,000 watts for 3,600 seconds. It's actually 3.6 million joules, which sounds like a lot, but the power companies will charge you, roughly speaking, a dime, about 10 cents to do that. So final question of the day. Let's see if we can figure out the cost of running a 60 watt light bulb, just a desk lamp, for 3 days straight, like a long weekend. You leave it on and you're trying to figure, oh geez, how much did that cost? Well, I know the power is 60 watts, but for house questions, when you're trying to figure out house consumption of electricity, you want to think of that in kilowatts. And it's actually not even a full kilowatt, it's 0.06. The time, 3 days. Don't go to seconds, but do go to at least hours. So that's 72 hours. And so I'm going to take the power and the time and multiply them together, kind of like we did at the very beginning of the day, power of 24 watts for 4 seconds. But here I'm going to take my kilowatts and multiply by hours. And when I do, that's actually my usage, 4.32 kilowatt hours. That's kind of like before when we were doing joules, okay? So that's not the same as joules. A kilowatt hour is 3.6 million joules. And if you wanted to figure out the cost, just take that 4.32 kilowatt hours, multiply by 10 cents each, it would only cost you about 43 cents, not too much. And so that's the end of our review of power calculations for Physics 12. And next day we're going to go over how to do Kirchhoff's laws and parallel and series circuits.